Okay, good evening, all the PhD students, and welcome back. So today still, this is a third lecture from Dennis' team, Dennis Zastavny, who is from University of Leuven. And right now, recently, we have a collaboration between the two teams. And actually, we'll kick off the research based on the graphostatics and focus on the timber structure, which is actually have a very special material performance and materiality. So this is the third lecture, which is about which will address the fundamentals of timber design, and which will also relate to our joint research project. So lecture starts by introducing the main characteristic of timber in buildings and outlines the conclusions to draw for the designing with timber. And the timber behavior actually is very special, especially in the future few years, not only in Europe, but also in China, where I think about it, which is the decarbonization process in the building industry. And the timber behavior is really special in fire, in types of construction and connection with timber, which will be reviewed today. So an analysis of the characteristic of the suitable structure system will then be presented and supplemented by the presentation of some relevant examples. So the design of efficient timber structure will be then addressed with the computational tool vector-based graphostatics VGS, which Dennis' team introduced last time. And also we put forward on the various of structure models, and also the tree branching structure system, the fan-like structures, lattice riders, and also CLT plan and the folder structures will be mentioned as well. And for each, the graphostatics interactive models will be shown, and structure explorations with the timber will then presented and showing the performance of primary structure and the different joints, elucidating the interest and the power of VGS as a tool for the controlled informed design of timber structures. So today's topic, back to fundamentals, which is the series of lectures and which is based on the performance-based research topic. And the VGS is really special from Dennis' team. So let's welcome Dennis Zastavny gave the lecture tonight. Thank you, Dennis, for your third lecture. Welcome.
So thank you, Philip, for this kind introduction. Good evening to you all. I'm glad to be with you for this third and last lecture for this series that Philip mentioned as Back to Fundamentals, dedicated to structural design. And the topic of my talk today, this evening, will be timber design. As you will see, timber design with timber or timber design is a quite technical topic. And so this lecture will frequently be more theoretical, and we'll be discussing architecture as well as structure around this. So let's start with an overview of the topics we will be discussing today, and I will be sharing the screen. So let's do with this. Normally you are seeing my screen, right?
Good, we can see everything. Good.
Okay, so perfect. Starting the presentation, and let's start with this. So as I mentioned, timber has a quite uncommon behavior, and we'll see that it is very specific characteristic compared to other kind of structure. And so the topic today will be first having a look on historical benchmarks, since this is in all countries in Europe, very important to understand what has been done before and where we are coming from to decide where we want to go from there. And then we will have a look on several topics that are timber anatomy and the related property that will be coming from this. The strategy for design considering fire and resistance of timber. Against this, strategies of design about water and durability of construction. Then having a look on design strategy according to mechanical resistance, and then design strategy about using timber product. From then we will see a series of examples in traditional timber architecture, in timber bridges, in contemporary timber architecture, and in CLT building. Then going to more structural topics, reviewing timber joint, high-rise building, just giving an introduction since this is a quite complex topic. Having a look on a structural system, among which this is the list that Philippe Yuan just introduced: arches, underslung system, tree branching system, phalanx system, trusses, lattice timber structure, and so on, to finish with corbel and bending or shear slabs with CLT panel. Then I will giving the word and the screen to my colleague Sylvain Rasseneur, that will be presenting a series of examples using VGS connected to what I just explained as a structural system, and that will be the topic for today. We'll keep some time for question and make a small break in about 1 hour. So let's start with this. And let's start with first with some historical benchmark. When you are discussing timber, this is one of the oldest material used by man for construction, and you see frequently this very simple primitive architecture that is put forward with timber. And what's kind of interesting is that in our manual, coming from this, we come quickly with Chinese architecture, with one of the older structural arrangement with timber, and with China putting forward this roof with quite steep slope as being something constitutive. All the building being built with timber, and only the basis with other materials as bricks, clay bricks, and masonry. In China, you have also what has been for a long time the highest timber building, with the pagoda of Fa Gong. And there's a counterpart in the Japanese culture, being the pagoda of Horyuji. This one being was of the oldest that have been kept in its current state. But you know, in the Japanese culture, there's a way of always rebuilding the construction to maintain them instead of maintaining in the current state. We have also kind of counterpart in Europe, for instance, with Norway timber architecture, with the Stavkirk in Norway, or Stave Church in our language, coming from the Middle Age. And going to other culture, we can find also in Russia kind of very huge construction made by with timber, with also palace of that time. Going back to Europe, if you are seeking the track of old timber construction, you can go in Old Ireland, in the Palace of Persepolis, in which you had a huge construction of more than 400-meter length, with the huge palace room, as you can see here, with stone columns supporting a timber construction. And these are not huge beams, so the span is about 5 to 6 meters in this case, and not being a huge beam, but a composed beam. So that's very interesting to have a look onto this. And this enables a new way to make architecture to raise from that time, since if you compare with things that are appearing in Egypt, for instance, you have not that huge span, and so the look of the plan of architecture are totally different. If you go to Greece, that is supposed to be a reference, since their stone temple are supposed to be a translation of timber temple in the way they are looked. If you are looking to this, you will see that indeed you can find traces of what could be the end of the piece of timber on some place of the building. And if you go into the technical construction, you can see that's a kind of pile, a superimposition of several timber elements. And as you can see, it just put on the precedent one without a complex arrangement in terms of structural design. For this, we'll need to wait for the Roman Empire. So we are here around the 5th century and seeing the first timber frameworks appearing, in which we have collaborative work between compression bars and tension bars, with a specific question arising from this. That's a question of the joints, the connection between bars. And if you are looking carefully to this, you see that the geometry of this connection is designed to develop certain kind of transfer of forces. So if you are pushing here at the head of the structure, you see that the way that the notches are made into the central piece of timber with transmit forces in compression, and that those connections are studied also in that way at the basis of the structure. You need specific arrangement for a specific joint also, and sometimes appearing the tension connection with timber that is managed here with steel, not steel, but iron ties or iron kind of boards in that case. You will see the system evolving along time, for instance, in this building, in which you see the interplays of a structure you know already, since we have studied it in the first lecture about graphic statics, with an interplay of compression bars and tension bars is a system of what will become later trusses. And so that's very interesting for this. Asking in the same way about studying carefully what will be the look, the appearance, the arrangement of the connection you have between all this member. So if you are going back to other system like timber, we are here in the before the Middle Age, about 600, 800, so the 7th or 9th century. We will see again the system of pile appearing for timber construction, and change will come later in the Middle Age. As you can see in the Middle Age, there are first more and more complex systems appearing with timber construction, with this example that are put forward by Viollet-le-Duc, that wrote a series of books about the medieval architecture. And what's very interesting to see is that if you are looking to what were the bridges at that time, you see very, very efficient systems that are quite connected to what we have seen before as timber framework from the roof or from Romans. You can see also kind of funicular structure appearing here, and the system being that efficient that, so we are in the Middle Age. If you are coming back to 300 years later in Switzerland, for instance, you will see exactly the same kind of structure appearing in timber bridges. So if we want to design something that could be innovative, we have to keep in mind all these findings that have been made a long time. If you are going to the way that construction were made with timber in Europe in the Middle Age, and more particularly this is in France, you can see the system developed from the 5th century in France as being the half timbering. In French, we have a very nice name for this. That's the name of colombage. That is a reference to a small construction that was made for a bird that is named colombe. So anyway, but you can see here this structural arrangement that is made with massive timber connection, and also the invention of what will be later called bracing in this typical look of architecture. You will see a quite complex timber arrangement with the notion of contact joint appearing more precisely in this kind of construction, and of course discussing today to digital fabrication, which convey this question of contact joints more intensively. Of course, you can see quite complex arrangement appearing with kind of farms building also that drive to very efficient arrangement. And the next step of this story is going back to this kind of the industrial development in America, and more specifically with the balloon frame system that has been designed as one of the first industrial timber structure, with what is called, as I mentioned, the balloon frame system, also called the Chicago construction system, in which you see very little material compared to the Middle Age that will be used for vertical bearing element, but quite repetitive. And a question of bracing that will be managed with some diagonal here, but most of the time you can use also the cladding with an angle of close to 45-60 degrees to develop bracing, and later on with the system that will be evolving towards the platform frame. These bracing will most of the time be replaced with panels, and that's still yet another way to design timber construction. With platform frame, you just have the structure corresponding to one story, one level, and they are just superimposing each other with the question of the global behavior against the horizontal forces coming from wind forces. And that will drive to other development. Of course, this system won't enable you to go very high, and we'll have a look on what will be the strategy that will be developed on a higher building also. So let's move from this to a timber anatomy related question, and to see what would be the connected properties to this. So wood or timber is coming from nature without significant transformation. That's true to a certain point, as we will see if we want to manage the issue of water, for instance, or with fire. Sometimes we'll have to transfer the material by itself. So the intrinsic qualities coming from the material depend on the species of the trees that will be used, the age of the tree, the quality of the soil, the altitude and the latitude, so the position horizontally and vertically around the earth, and also the treatment that will be provided to the material. Since this is a material that is natural, you have a high variability of properties. So that is in contrast with most of the industrial projects we have. And so this is why for a long time, this material has been disregarded by engineer and architect in the industrial times, but also with specific strategies with, for instance, wood-based material as glulam, laminated wood, and panels will be reinvented, a new kind of architecture based on wood-based material but produced by the industry. And the last but important element are that putting forward the grading of wood, so about resistance. We have a European system that has been developed for this, looking to derived product, joint techniques, and also digital fabrication. All this brings a new life to this material, timber material. Also, as timber is natural material at the origin, you can have a possible sustainable approach to construction and to material, but it will depend on the treatment we will be providing to the timber, and we'll be discussing this in the next slide. So timber is coming from the trunk. That is the only part of the structure that will be used, of the timber of the tree that will be used for structure, and the rest won't be used. And if you are looking more closely to a cut into the timber, you will see that there are several zones appearing. And if I start from the beginning, you have the heart of timber that's called medulla, but then you will have the heartwood, sapwood, and then an interface layer that is called the cambium, that is the crowd zone of the trunk of the tree. And actually, the cambium and the layer just after, that is the bast, will be the only layer that are truly living. If you start from the beginning, the sapwood will be quite dead. The heartwood would be quite dead. The sap would be still living, but not that much. We have still some nutritive flow that will be met into this. And after these two zones, so that will be the cambium and the blast, that are the zone where the tree will be growing, you will be able to see the bark, that will be the dead cell coming from the protection of the timber. This is important to put forward for several reasons. First, you have annual rings that are appearing. So each year is corresponding to a ring. We will see more in detail what this means about these rings. And also that we will see difference in terms of behavior between the center, the heartwood, and the sapwood. And sometimes we will have to make different decisions about using or not the sapwood all around the heartwood. And I will discuss this later, since this has a cost. From this, we have different families of timber. We have softwood and hardwood. Softwood example are spruce, pine, larch, Douglas fir or cedar. Hardwood as oak or chestnut, beech, birch, locust, for instance. If you have also tropical timber that will be used most of the time for the window framing. About structure, we'll be discussing most of the time about softwood due to the specific property I was discussing later, and hardwood with specific connection or reinforcement, as well for resistance against forces than for fire also. Going more in detail about this, you can see that there are kind of series of tubes that are assembled. And if you're looking from this to this is connected to a tree. This is corresponding to one annual ring of timber. So when the winter is finished, the timber will be more and more living, and you will have growing cells appearing, and that it will be slowed down again to going back to the time of the winter. And that will be shown with what you will see with your own eye as ring coming from 1 year growing of the timber. What you can see also is that you have indeed this kind of tubes, and this tube will explain that the behavior of timber will be quite different according to the direction you are looking to. If you are trying to put some forces in terms of tension force along this tube, and if you have no loads in timber, this will be very resistant. If you are pushing on this tube as with tube, steel tube or anything in the true scale of a building, will be buckling, and so this will be limiting the resistance compression. Of course, if you have nodes appearing in this anatomy, this will be limiting the resistance tension also. So differences appear due to this anatomy. If you are pushing perpendicularly to this system, you could crush these tubes that will be less resistant in perpendicular direction than in the longitudinal direction. And if you are putting tension forces, these tension force will separate this tube quite easily, and that will be the weakest point of timber. So this anatomical view on the left is connected to softwood. If you are having a look on hardwood, you will see that the anatomy of timber will be slightly different, and that will be explaining that this timber will be more dense, more heavy, and will be more resisting also, but will be growing more slowly. And again, you can see this annual ring of growing of the tree. So from this, we learn already some element about the behavior of timber. And indeed, if you are comparing forces depending on the direction, if with bending you can have 100% of what would be the class of timber. If you have only compression, you are just at 85–90% of this resistance that is shown with the blue arrow. If you go to tension and traction along fiber, you can see that the resistance will be limited to about 60%, and this is due to presence of nodes into timber. But if you are perfect timber, you can have up to 2.5 the resistance you have in compression. So these arrows are in scale, showing what would be along the fiber the respective compression or tension resistance you can deploy on this material. Of course, if you are going to press perpendicularly to the timber, you see you just have 10% of resistance, and with tension is just a little 2% resistance. That will be the weakest point of timber, and that will drive to specific attention to structural problem. If you are going to more in detail in the anatomy, you see that there are several components of timber with cellulose, hemicellulose, and lignin, and some extract. And this extract will be all the difference between a timber species being durable or not durable, resisting to fungi and to wood-bearing beetles or not. And that will be explaining also that you have this kind of extract in the hardwood and not in the soft wood. From then, going more in detail, you see that timber is composed with carbon, oxygen, and hydrogen with some nitrogen. And carbon, oxygen, and hydrogen are translating what will be the constitutive material in timber with carbon and water, and also which explain why you will have a molecular anatomy that will be close to what we have in other fuel materials. What is to be put forward also is that in this you have oil, H2O that will appearing as water composition, but also water that will be more or less free into timber, and that will represent a true problem. So as a summary up to here, we have several components, and with carbon and oxygen and hydrogen, we'll see that timber will be a kind of natural polymer, so the kind of plastic that will be interesting, since you can associate a true plastic to this natural polymer. And we have also fiber that will be hollow and that will be transporting sap and nutriment that could be a problem against the durability of the timber. We can see that depending on the family you are belonging to, between softwood, hardwoods of tropical timber, will have different uses, and most of the time some softwood will be lighter, would be quite resistant, and will be preferably used for structures. So framing, trusses, and so on will be made most of the time with softwood. Hardwood are harder and very heavier. So most of the time we'll be using for this for furniture and stairs, but also with local reinforcement in structure made of softwood. If you are looking to the structure of a very old and resisting building, hardwood will be used in the timber frameworks of cathedral, for instance, and more particularly, as we will see, it will be chestnut that will be chosen in that time. So most of the time, we'll have to deal with softwood with structural system. So what about the design strategy that will be connected to fire and resistance to fire? If you are having a look on what is the chemical composition of timber, you are taking CO2, so carbon, global warming material, associating with timber, you are putting some energy in a form of light to associate this to a kind of sugar, glucose, as C6H2O6. That is quite a formula that is put for wood for timber. And this will produce also oxygen. And this is why you can say that timber is the lung of the planet, since it produces oxygen when associated CO2 and water. This principle is named vegetal photosynthesis and is a chemical reaction that needs energy, and the energy will be provided in the form of light. If you are going into the night, you will see that every trees of plant will be breathing as we do, and will be using his structure to be associating to oxygen and producing the reverse reaction, producing CO2 and H2O. If you are making the balance into it, this reaction during the day will be more important than the reaction during the night. And you can see that also that's a very important aspect that timber is using CO2 to be built. If you are having a look on biological attack as fungi of wood-boring beetles, you will see that they will take wood is the general form, associating to oxygen as they are breathing and they are eating it to produce and to release again CO2 and H2O and produce energy that this fungi or beetle will be using for their own growing. There's another kind of a similar reaction is that when you are having fire, this is exactly the same equation that we have seen with biological attack, and the energy that will be released will be the energy that will be using for heating system. And this is why this is called an exothermic equation, in which you are this time releasing energy. So wood is a combustible material and a flammable material due to its anatomical composition and due to the fact that at the end, the global energy producing will be positive. But if we look more in detail into this, is not that easy. First, indeed, comparing wood to other fuel material, you can see that the structure is quite simple, quite similar. You see here wood appearing, and you see here coal, anthracite, and gases without the oxygen yet. And this full burning of timber would produce in between 19,000 and 21,000 kilojoule energy per kilo of wood. Now, to put some fire into timber, you need some specific condition. You need a combustible material, and timber is that kind of material. You will need a oxidizing agent as oxygen, for instance, but you have oxygen all around us. And then you need a third condition, that is to be providing some energy to the system. And the energy can be produced as fire or the temperature that could be provided to the system. So more precisely, you have flames that will be put on timber, or you will have a temperature that will be high enough to put this timber in fire. We'll be answering this question of the temperature in just one moment. So for having timber burning, and this is the case in a building, also you will need fuel, oxidizer, and also the energy that has been to put to the material as in the form of flame or as temperature. If you're looking to the curve of the rise of temperature in a building that will be burning, you will see that you need to put some energy in the system up to a certain temperature, and that won't be the timber or wood that will be burning first. It will be papers and all the tissue that could be burned first. And as soon as we'll be reaching a temperature that temporarily will define at 400 degrees Celsius, all that would be in timber we start to burn. So in the phenomenon of fire in the building, as soon as the temperature is enough to reach this 400 degrees, you will have the time of the flashover. So it will be the generalized flaming of the building, and then the temperature could rise quite heavily to reach 1,200, 1,300 degrees Celsius degrees for this temperature. And then when we have no things to burn, temperature will slowly goes down and stop with this. So if you want to ignite, put fire to timber quite quickly, you need a temperature of 400 degrees if you want to do it quite quickly. And so for this, you don't need to have flames. It means that as soon as you have 400 degrees temperature in a building, everything that would be in timber this start to burn, even if there are no flames going to it. If you have more time, you can put some fire at the temperature of 400 degrees. If you have a long time to put this fire on timber, and also if you have flames that will be put on the material. And even with a lower temperature, but it will take a long time. So keep in mind 400 degrees if you want to put fire in a quite short times. If you are looking to the rise of temperature into timber, you will see the temperature will be rising and having a step here in which temperature is maintained to 100 degrees. It's a temperature in which the water that is part of the timber will be boiling and going to gases, and from that time the temperature could rise. And this shows that water will have an important role to play against fire in several forms. We won't recommend to use wet timber, but since we'll be drying in any case, but material containing a certain amount of water would be very useful for this. Going more in detail, you will see that I mentioned that you need to provide some temperature or energy. So before that we raise the temperature of 300, 400 degrees, you need to put some energy. And so there's a question, that's the reason why timber is not flaming alone. You need to put some energy to a certain temperature to get an exothermic temperature. When this is done, something very interesting is that the timber will be burning and will be producing coal, and this coal will be met all around the timber material. And also we'll see that due to very specific properties as well of timber and with this coal, the temperature inside this material will be maintained quite low. Here you see with the timber burning of more than 400, 500 degrees, it could be 1,000 degrees. The center of the section will just be, in this case, 32 degrees Celsius. So it means that this timber will be maintained with all its properties. And this is maybe one of the only material that can have these properties, and that's very interesting, since the other material will be changed with temperature, but the inner part of the timber won't be changed, and that is why timber could be a very interesting material against fire, even if this is a material that can be burning. And the other fact is that the speed in which you have this coal being formed on timber can be precisely defined. So you can just calculate the remaining section into it, depending on this speed of burning rate. And you are able to calculate very easily what could be the performance in time of timber against fire and against loading. And that's not that easy with steel, for instance, or with concrete, for instance. So you need to, you will have a burning peripheral zone, and this will be reducing the load capacity, and you need to oversize, and the burning rate will be in between 0.6 and 1 millimeter per minute. So providing some centimeter protection will be guaranteeing that the system will be resisting fire. What I mentioned is that if you are comparing the heat transfer coefficient of wood or timber here being 0.15 watt per meter and Kelvin degrees, you will see that this is far less than concrete, steel, or clay bricks, so that the wood itself won't transmit the heat that easily. But as soon as this timber has been turned to charcoal, we have such a low coefficient that will be below the limit in which you have insulation material that will be appearing. So typically, insulation material have this heat transfer coefficient of 0.040 watt per meter Kelvin degrees, and timber will be below. Of course, this charcoal will be cracked and will be sometimes damaged, but this shows that timber is protecting himself with the production of charcoal, and that's the explanation of why the temperature can be maintained quite low inside the system in itself. Looking to the burning rate and the time you need to put some timber in flame, you will see a very obvious mechanism in which the density being higher, the more time you will need to flame timber, and the less will be the combustion rate of the timber. So we will see that choosing heaviest timber element will guarantee that it will be resisting better and better against fire, in supplement to the protection mechanisms that timber have against construction. And so you have a typical rates. You will see that lighter material as plywood and wood panel based. Wood-based panel would have higher progression of fire coefficient. And if you have solid soft wood, also you will see that this will be less for soft wood and yet less for hard wood heat. We'll see also difference between solid timber and glulam timber, since glulam seems to be better against fire, and this can be explained quite easily with the parameter of these burning rates. And one of these parameters is you will be comparing the surface and the volume, and the most is this proportion between surface and volume will be the easiest would be to start combustion and flame to be spread. So the objective would be to have less crack, and you know that when timber will be drying, you will crack appearing. That won't appearing most of the time in glulam, and also in glulam you will be removing all the cracks and so on. And so for good resisting to fire, you need massive section of timber. With no difference, it will be glulam or massive timber, even if this behavior would be better for a glulam. So you keep in mind it was the question of the proportion between surface and the volume, and the easiest way to protect timber is just to withdraw surface to the presence of fire. So you can using this by using panels made of lime, for instance. You can use specific paint for this, or you can include the timber into other component of the architecture to be protecting timber against fire. You will see that there are several steps. Actually, the timber does not burn itself. It will be decomposed in several products, and depending on the temperature that will be met for this timber, this decomposition product will be more or less flammable. And this is why you need a first process in decomposing wood with energy to put to release this material that will be able to enter into burning step. So several parameters to put for wood. The type of wood, you know that indeed putting some log, timber log won't be that easy, but putting some small piece of light timber would be easy to do. So the type of wood, the section of the element, the moisture content of wood, and possible protection of the surface will be a governing parameter to take into account. What's about connection? If you are looking to what's happened to steel that is used for connection in timber, at a temperature of 400 degrees, you will see that there's a loss of properties of about 40% in steel. And that's a true issue for me on timber, since when you will be losing that much properties of steel when at the temperature where the timber is just starting to burn, you will have the steel that is just disappearing and totally disappearing with all the building has been put in fire. And so that's a true problem. And sometimes you need to multiply the number of connection rods you will be putting in timber. And also this can be the factor that will be giving the dimension of your member. You need more place into your member to put some more dowels or bolts into it. And so what will be governing the dimensioning of the system won't be the resistance against fire of the member itself, but the resistance of the connection. So each connection being used with steel needs a specific attention to this. There are some formula here that will be showing that at a temperature of 40 degrees, you will have lost of 42% of the strength properties and a loss of almost 30% of the elasticity, so the deformation of the system with steel. So did show that timber against other material as steel, for instance, with steel structure, timber will have advantage, and indeed that this steel will be the weak points of construction against fire. I have to put forward that depending of the temperature, in the first state, you remember that temperature in timber was raised up to 100 degrees. You have also a loss of properties in timber itself, but you know that these 100 degrees are not met all inside the structural member itself, but you see that indeed, as soon as timber dries, it loses also a part of its properties, as well of traction, only 10%, but compression is suffering more about this loss of water into timber. So I mentioned about this speed of progressing limit of the cold zone around timber burning. And as you know this, you are able to calculate what will be appearing as a resulting geometry of a member when you have fire. And indeed, the stake will be to have less possible surface of timber. And if you are to make the choice of very complex geometry with a lot of surface, that's very nice to see, but it's a disadvantage against fire. So what could be the summary about the design strategy against fire? So fire in timber can be easily controlled. You can oversize section using this beta coefficient that I showed just before. You have to reduce the exposed surface or choosing for most massive section, and you can protect this timber with material having a high water content, as lime, for instance. If you have steel connecting rods, you have to choose the less massive steel elements since they are driving, conducting heat into it. So you have to choose dowels or nail instead of boards, for instance, as connector. If you want to protect locally, and you can protect the steel connecting rod, for instance, if there are no head as boards, but if you are using dowels, you can protect timber using hardwood, for instance, for local protection. You can try to use timber to timber contact joint. On that case, you won't have to suffer what's happening to timber. And you have also fire retardant product that can be used on timber, since it will be changing the chemical reaction, but it will turn your natural material to a material that won't be that natural, and that could be a problem at the stage of the end of life, and that's for sustainability. What now about design strategy against water and the durability in timber? So you know this equation. If you are looking to this, you see that indeed timber is a long file of carbon associated with odors, and you have kind of a limit that will be either OH or H. And there will be a natural connecting junction that will be between water and in between timber. So we'll have water that will be attached with a low force connection, and that's meaning that some of the part of the water that will be coming to timber will be changing the molecular composition, and from then the volume of the molecule will be changed, and that's a problem against timber. So we have kind of file of this long series of polymers. So it's a glucose polymer, a sugar polymer, and we'll see that you have kind of lines of polymer up to 3,000 or even 10,000 molecular unit that would be associated to do the nature of timber itself. What about water? We know that we have tube and there could be water in the tube. We know that this chemical composition of timber can attract water also, and you have water that has been used to build the timber in itself. So water is a material full of water. Timber is a lot, have a lot of water into it. And depending on the fresh cut timber or even a living timber, you can have up to 600% water into timber. If you are going to go inside a building, you will see that the equilibrium is around 12% timber. So you have to moving this water outside of timber, since indeed you will have a connection of the question of water with the fungi and also the beetle that will be attacking timber. The third end of this water, this free water, is just the water that is running into the tube of timber. And as soon as you cut the timber and you put it vertically, you will see this water just flowing down from this tube. And so it can be eliminated very easily. If you are going more in detail with the remaining water, you have the bone water into a timber, and something that's very positive is that if you maintain timber is low in a, how to say this, in an environment in which we have low moisture, you have low water into the air, the timber will be balancing the natural equilibrium of water and will be releasing this water. So you can dry naturally a part of this timber. The fact is that it will be swelling radially and tangentially, and that could be an issue that we'll be discussing just after. And combined water into timber itself won't be released if you are not burning the timber. So we don't have to take care of this content of water. What would be this variation of dimension? Timber is not reacting to heat for dimension as concrete or steel will do, but will be changing dimension according to the level of moisture in the air. And as you can see, this change of dimension will be more connected to this radial or tangential dimension. I show this since this will be defining the way that cutting part will be reacting. If we have this kind of section, will be impacted by radial. If you have this kind of section in the other direction, it will be impacted due to the tangential dimension. And you see that if you have 1 unit of deformation in the longitudinal direction, you have 10 in the radial direction and 20 in the tangential direction. So that could be a true issue, and indeed this rate of changing is about around 0.3 to 0.4% variation of dimension for 1 degrees, 1% variation in the moisture of the air. So it means that when you have internal level of 30% of moisture in the air, going in the summer, for instance, and going as high as 20 in the winter, for instance, you gain 30% in the air moisture, and in timber, you have a change of about 6% moisture in the timber itself. And if you are multiplying this variation of 12 minus 6 giving 6 by 0.4%, you have a change of dimension of about 24 millimeters by meter. So if you have timber plank that are put on the ground to protect it, between the winter and the summer, you have 2.5 centimeter difference of dimension. And so if you don't take care of this, you have 2 problems about the behavior of timber. Anyway, but this problem also appearing in structure, you know that timber is drying with time. This drying will produce crack into timber, and this crack indeed will change the mechanical properties of the section. If you are cutting this with some specific cutting into the section, this will be controlling the way that timber will be changing dimension, and you are putting yourself a kind of hole into it. But also this shrinkage that will be linked to timber will drive some specific problem at joint connection. And this calculation that has been forwarded by Tribullo and Calvi in 2001 show that in the case of the timber framework, the dimension, the change of dimension could be higher due to the change of moisture compared to the deformation we'll get against loadings. So the structure will be more deformed by the play of water, let's say so, than by the loading by itself. And of course, if we have connecting timber to timber connection, this change of dimension will be changing the contact you have between the several elements and could drive the forces that could be transmitted in the timber that could be very different and attracting some force in some member instead of other timber. Even with connection, if we have a steel plate or two different directions of timber, so these are about two different directions of timber, the one being vertically and the other would be, let's say, horizontally or almost, or with the connection with steel plates that won't change of dimension with the temperature, it will drive a timber to change its own direction and you will have cracks appearing in the joint of timber. So that's needs a specific attention since this crack is appearing perpendicularly in tension of the direction of fibers. And this is the weakest point of timber. So that's indeed a point of attention for this. What about the variation? You see that's a kind of equilibrium in timber that is connected to the moisture you have at timber. And so the idea would be that if you want to control this, you have to find the level of intrinsic water that will be corresponding to the condition in which the timber will be used. And then you will be lowering this shrinkage phenomenon appearing in timber. So classically inside we are around 12% for timber from a framework, for instance. And to reach this level, the question will raise if we want to dry artificially using energy for this or not, since it will change the balance of the environmental impact of your timber. So depending on the use, if you're using cladding or decking, or if you're using window frame or frameworks, or using a parquet on the ground, for instance, you will have to choose normally different level of moisture into timber. What's very important to see is that fungi in wood come around 20%. And so if you have a timber wood that has been dried to a lower level of this, fungi and after wood boring beetle won't attack timber. So the best way to protect timber against biological risk would be to dry it, with the question naturally or not naturally. If you want to dry naturally timber, you won't be able to go below 18%. So that's a question you have to balance into the design. So what's about the strategies? You know that water is attracting fungi and also wood-bearing beetle, but also that water will impact the structural behavior also. So you have to make a choice. If you want to just protect your timber, you have to dry timber, and that will be raise the gray energy. Or you can use an artificial protection for timber and not drying timber, so you will have crackings appearing. And in this case, you have to put some chemical timber, and it will have an influence in terms of environmental damage. So, so you have to make your mind about all this. And indeed, you have also this characteristic that timber with the sapwood won't be resisting at all. So you have to decide if you want to remove it or not. And depending on what would be the hardwood in the middle, you have will have resisting or not resisting at all timber. And for instance, you see, so the smallest would be the more resisting. That for in terms of hardwood is starting here to here. You will see that chestnut would be the best resisting hardwood, and this is the one that has been chosen to build the timber frameworks of Cathedral, for instance. You will see also that depending on the nature of timber and the fact that the sapwood and the hardwood won't be different, You will have attack that would be running through the timber or not running through everything into the timber. That some insect attack some kind of timber, not other. I won't go into detail about this. You have to keep in mind. But what's important is that there are use classes, dry wood only or hotted wood that would be in seawater or with a contact with the ground or interior and so on. And you can match, that's just for the detail, I won't enter into this. You can match the durability class of timber that we have seen before with a class of use that could be develop in timber, and that's a way to guarantee the good standing characteristic of timber. You have preservative treatment, as I mentioned, so it could be metal source, it can be organic product, and could be heat treatment also, but that will be changing deeply the resistance properties, or you can use other kind of chemical, but you won't turn your natural material to let's say a chemical material, and that's a problem at the end. You have also protective, and not preservative, but protective, so protective around timber as painting strains and holes, but this requires maintenance, and that's another kind of questions. So next step will be discussing the design strategies for mechanical resistance, and then we will go moving to the case studies, but I suggest that maybe we can do a small break of 5 minutes here to have some rest and drink some water or coffee, and then starting back with this.
Okay, great. And let's take a break.
So let's have a break. See you in 5 minutes.
See you.
So the most of the theory has been done right now. Let's move to the question of resistance, and then we'll be back to some case studies. There's a question of grading of timber appearing, and you have several classes that has been put for wood, in any case in the European system in which I am belonging. I won't go into detail. And as you can see, there are several properties that are known as early as you know what should be the strength class you are belonging with your timber. And you can see on the left, for instance, that 0 is mentioning the direction of the fiber, 90 is at an angle of 90 degrees with the timber. K is just telling that it's kind of a way to calculate the values that guarantee that 95% of the element will be resisting. T is for tension, C for compression, and so on. So as soon as we have this grading that has been put for wood, that's a way to guarantee the properties. Of course, this figure I'll show you, actually, it's a little bit different since you have several systems that has been developed, and in the Eurocode, the reference is Hankinson, in which you have this kind of curve that could be met, for which we have a loss of resistance from the sense of the fiber and the sense perpendicular to it. And so that's a point of attention when we will be designing with different direction of timber. The same exists with hardwood, and you see that indeed the values are very higher that you have in timber.
Dennis, I think, could you please share your screen?
Oh, sorry. I found it was raining also. I'm starting again with this. Oops, sorry. So sharing the screen. This one.
Okay, here we go. Please.
That's okay. I'm sorry. So we start again from that point. I thought it was okay. Can you see the screen?
Yes.
Okay, so starting again from then, sorry. So I was mentioning quite quickly, since the time is running on, that there are a grading that is proposed for several types of timber. I was mentioning about the resistance here, characteristic 95% of element that were resisting, 0 for the sense of the fiber, 90 for perpendicular to fiber. And I was showing the laws that could be governing the resistance of timber according to the direction we have. That could be quite lower indeed in the perpendicular direction. So I was mentioning also that of course the level of resistance is higher for hardwood, and also in between with glulam, since glulam is just extracting what would be the nodes of timber, a whole singularity of defect, producing a better material with material that is not that efficient at the very beginning. What has to be mentioned is that timber in compression in blue have plastic behavior, but almost a fragile behavior in red on the curves. And if you are working on designing the structure, you have to be attentive to the capacities to redistribute forces, and even more if you are working with plastic design, as we do. So the plastic possibility to redistribute force would be linked to the properties of compression or the properties you can deploy at the place of the connection, and I will be discussing this. So in the European system, we will have ultimate state design. And from this, you have to guarantee the force. And you will see here for timber that you have a security factor that will be applied on timber, and that you will have a modification that will be attached to the duration of loading. So to be more precise, you can see that if we have long-standing permanent loading, the resistance of timber will be reduced to 60% of what you have in short term. And if you have instant loading, it can raise up to 110% of the resistance. So in any case, you have to take into account the fact that the timber is losing its properties along time, and this will be connected to the question of moisture again, so the question of water into timber. So it's wise we take that time to discuss this. So you can see here on a curve that you have a creep phenomenon, so long-term additional deformation that could be 300% of the deformation that you have in the short term, depending of the variation of moisture you have on the short terms. Now, what's about design strategy using timber product? The first idea is to use solid timber and properties depending on species of growth and shaping modes, if you are cutting the fibers or not when we are sewing or reworking the surface of timber. And that's questions. You have also the length of the timber that could be limited, most of the time around 6 meters, and section could be limited also. And the fact is that you have kind of industrial produced section. I don't know in China, but you will tell me about this. In Europe, you have most of the time the section that will be 2 to 3 times higher than the width, and the American system, it can be up to 10 times. So you have to design totally differently the structure according to the fact that you will have instabilities that are linked to the very high section as you have produced here. Timber product as glulam, as LVL, so as for instance, this Certo panel will produce very high resistance materials, and you have also the rated product that could be used, or even composed section with small section that could be reassembled. Here you have the head of the wood that was on side that will be put on after cutting in a cross on the outer part of the system. So it was the zone where the bark was, so the outer zone. You can produce a very efficient system, but this one were not always interesting from the financial point of view, as we have massive system appearing on side. New product as panels for as not panel here, we have composed system with a lot of resin into it, could have also very high properties. And you can have also panels as oriented strand board or multiplex panel that could be used to assemble your system. So what's about this? It depends on your philosophy that we'll be discussing on the system you will be approaching in the other types. There's also product that could be chosen for long-standing holding at the external zone of the building, for instance, with the solid panel. And something very interesting would be this timber product as CLT, cross-laminated timber, that we'll be discussing, and that representing a true revolution for timber. So let's move this time with to a design example, and starting with traditional timber architecture. I won't showing you Chinese architecture, but more Western architecture. I mentioned the Staff Kirk that was produced, and there's a very clever assembling of structural element to produce this kind of building, and we have to learn a lot from this. Indeed, in the terms of design, you can have a look on what's appearing in Finland, that is a region in which timber is very widely used, and learn from this. You are protecting timber from the ground with stone. You are protecting the highest part of the roof with timber. We have several elements that will be putting away the water from the element. You have places that could be replaced, and this is protected with strain. This is not a painting, but a melange in between the oil and the paint in this case. And there are parts that will be different, that could be replaced, and other that will be maintained. So that's kind of element. You can have very classical architecture also appearing with timber. This is not a stone at all. This is timber. And when I was mentioning the fact that we can turn a system of timber to stone for the appearance, the origin, where several number of examples are still timber. So with this example here, you can see the plank on the facade, and you can see also that the assembling of architecture is also a way to protect specific zone of the building, close to the roof, close to the ground, in the angle, and so on. And these are these examples that are speaking from. If you are going to timber bridges, you have this system that's quite very old. So that's another example in painting of the Middle Age by Dürer, if you are known this time. And you can see here an efficient system using funicular, but also protection of timber with a roof, and also protection with kind of facade on both sides to avoid the rain to go to the structure and to make it getting less efficient with the time. So this is another example coming from Switzerland, and what's very interesting is that you have a kind of lattice structure, and this lattice structure with connection with lowering the length that could be buckling. So that's a very clever way to assemble several elements, and we'll be discussing this kind of structure in the example that will be following. Again, you will see the role of the roof and the role of the facade, and in that case, the rain is not able to touch directly the structure, and that's for timber quite a clever version, and you know already this version indeed. More timber design, and you can see that indeed what is truly the structural part of the system is a very small part, and the rest of this is just designing something to protect what would be, let's say, the core of the structural system. We mentioned the fact that we have to protect the timber against the contact with the ground, since these are worse condition for long-standing system. You can see a traditional version coming from the Chinese city Pinhao, and you have the kind of modern translation to this using a basement made of concrete with steel connection, and the timber that's not touching the ground. More protective assembling like this. So this is a part of the design in which we have to consider every contact with water that could be a problem in the way you design the structure. And you have some example of this in which you have been avoiding the contact and using steel connector to take some distance with the ground. And also you have the geometry in itself that can be useful. Sometimes you can use protective element. Here you have a thin layer of zinc that is put on timber to protect what will be the fragile zone. This zone, when you have fiber appearing, is the worst indeed. And you can see in this example, or in the example here, where there are specific sheets of metal plates that have been used to protect the global environment. You can see also the sheet of metal appearing here on the horizontal zone of timber. And that's a way to guarantee the long-standing character of timber. In this example, you see that the connection with the river is made with another material, and that you have also protective element that will be put on the structural system to protect it. And you have also the fact that you have a kind of cantilever on both sides that will be protecting the element in some part against the rain. So that's clever design in terms of durability. Some contemporary example in architecture, just to discuss what would be the strategies, again, finishing the system and protecting them. Timber can be something that is not appearing as timber in some example. You can use a thin element of timber of even steel in the place you are not able to guarantee that that timber will be long standing, for example. And you can associate the timber screen made of cement, for example, to raise the level of performance of floors that could be met. You can protect it with panel that you can remove and replace, or you can protect it with kind of cement of lime protection with timber. You see that the fact that distance from the ground, distance from the roof, and overhanging roof that will be protect the element that could in any case be replaced later. These are kind of strategy you can have. You can also have very different elements. We are in Switzerland here. The problem of Baumschlager and Eberle, or here back in Finland. And you can see small attentive connection with the roof, with the angle that would be reinforced, or with the contact with the ground, in which you are trying to protect timber against what could be the risk in terms of long standing of the structure in itself. Well, other strategy with paint in this case with again overhanging roof, or this massive panel I was briefly showing here to guarantee that it will be long standing. In other case, this panel won't be able to resist a long times. And you can see indeed that the appearance of timber could be very different according to the strategy we'll be choosing. Again, here this part of building is protected from the ground with a parking zone made of concrete and overhanging roof system. But what is interesting in this building is that you have protective layer in red and green that are not quality wood, but that can be replaced a long time. And when you are too much exposed, you can just use another material to protect it in some places. And that could be a real strategy that will be defining your architecture. That's another example in Finland that would be a massive timber development. That is quite another story. Timber is the occasion to play also with light of raised material, with a very detailed work that you can do with this. So very nice architecture. It's not always massive architecture. And we have a lot to learn of this small pavilion. Here is not in France, but also here we are in Finland, with the way that these elements have been assembled in terms of appearance and in terms of long standing for the system. So that these are very nice examples. Choosing for massive timber, you can do it only in several places. Here we are in Switzerland, where there are less moisture than other places in the world. And you have an example in which we will be using this massive system. Here we are back in Austria, in which you have a massive system that is being used with the question of resisting water. You see that timber is changing in appearance, but with very nice architecture. And you can see on the side a traditional connection that will be reused for this kind of timber construction. You can deploy imagination to devise what could be the system of timber, and with properties that could be totally changing depending on the scale of the element you will have, or very informed engineering approach in which you can take the advantage of timber to develop very interesting system on the long time. And with strategy on protective that are linked to timber, here you have wide strains that have been applied to timber. You can see the internal structure, but you're still protecting the timber. Also to say that a region in the world, for instance, here in Austria, with the Vorarlberg place, in which you are developing very interesting architecture made of timber, but using traditional way in the way. And also that timber could be a very technical material. I mentioned already several systems against fire, water resistance, and changing dimension. We didn't discuss about insulation, about controlling moisture into the building, about connection, about managing the topics of acoustic that can be managed. So it drives to very technical approach and very technical detailing. And that's the part of the essence of timber. So let's have a word of CLT buildings. So CLT, as you know, are this kind of panel with crossed direction of timber, and it drives very efficient system that could be a device as shear walls made of concrete. And that could drive very interesting approaches in terms of development and also specific design approach, as I mentioned also in the second lecture, if I'm not wrong, about Stirling time modeling into this kind of model, and also reinventing structural system here with folded plates, and that will be an example that Sylvain will be presenting in the next slides with what could be taken as advantage of this kind of material. Just a few words about high-rise timber building. One of the first was this one in 2009 in London, was 7 stories of timber that were put of a classical concrete layer that could very speed the construction. You need only a few weeks for each story instead of weeks for the whole building. And so this has been assembled very quickly, and also having a very positive impact on the global warming potential of the material. Just to show you what has been developed was specific jigsaw connection between the walls and the ground, giving this appearance as a structure, and you see the connection system that will be developed. But at the end, you cannot see any timber in this building that has been protected by plasterboard at the end for fire dimension. You have also a very other approaches that can be followed for designing high-rise timber. And here, this is not linked to shear walls, but to, let's say, more classical post and beams systems, driving to yet another kind of appearance in the building, and with a specific attention to developing the bracing of the system. And you can also go with let's say mixed or hybrid construction using steel column, for instance, with timber flat roof, or using timber for the frames and columns, and using a concrete slab. These connections are possible on a different scale of building. To answer the question, what are the tallest buildings in the world today? You can see here several examples of the top 5 elements, with the highest building made of timber is currently 86 meter, and that's just released in the US. If I'm not wrong, was Austrian design office, but I have to check this. Well, just a few words about timber joint. Timber joint are contact joint or are using steel connector. From this, you have different behavior against fire. As you know, you have to choose for this kind of dowels instead of bolts that could be exposed to fire. Here you are able to cut at the limit of timber, or even to put some kind of protective element of timber, and that will drive you the very complex issue of designing this connection against fire, but also against forces in between connection made of steel and connection made of contact joint. And what's important to mention about the global behavior is that according to the dimensioning and the respective dimension of the system, you can deploy ductility, so plastic behavior of the connection, are very, very low. And to characterize this a lot, if you compare a connection that is being with glue, so this is strain stress deformation, so you have deformation here. Or if you compare to nails, you can see that nails could develop very plastic behavior, but very fragile behavior if you are using glue between members. and doors and bolts are in between. So you have to be attentive to this if you want to deploy a good structural behavior against robustness. And more example of this kind of connection. Now, let's have some short presentation of some timber structural system, and I will be giving the word to Sylvain just after this. The first stuff you have to say is to make your philosophy about what you are looking in terms of objective. If you are looking to material efficiency, or if you are looking to redistribution for plastic design and redundancy in structure, if you want to follow up architectural constraints, if you want to dissipate energy against, for instance, earthquakes, or if you want to guarantee fire safety, acoustic, and carbon sink in your building, you have totally different philosophy of structure about this. If you want to guarantee fire safety, acoustic, and carbon sink, you go to massive timber construction with shear walls with bending slabs made of CLT, for instance. If you have the problem of earthquake, you can go to traditional Japanese or Chinese architecture or covered system, as you have seen the very first bridges, in which you will be dissipating energy in the connection and not damaging the structure. If you have to go to architectural constraint, you have to need regular forms, and then we go to frames or post and beam systems. If you try to look for redundancy, you can have to go to trusses, lattice trusses, post and beam, or arch system, in which you can develop several mechanisms into the system. But going to material efficiency, this is more with bars and surface system. I won't be discussing surface system as vaulting and shell, that's quite particular, but with bar is a fan system and branching system, for instance. You will have several examples of that kind that will be put forward. So let's have a look on this as example. You remember I mentioned the dual representation between truss analogy of bending system. You will see again this kind of system with truss line, fan like support, and tree branching system appearing in the example I will be showing, and the example that Sylvain will be showing inside of VGS. And so here are some true study cases that are really existing, starting first with arches and Edershlung system. This is a kind of system that has been developed with the Grubenmann brother that will be very inventive in the design. So here you have a kind of truss in a roof, integrating an arch, and also having the global dimension of a truss, but with mechanism in which you can follow the arch into it. So you can invent this kind of very efficient structural system. You can do the same with Edershlung system using tie bars and associating steel with timber, in this case of bridges. So you can manage as well a system of compression and tension system, but also a bending system in the gather here, and the most to have several different objectives. So more you can be efficient and also guarantee some redistribution of forces. Here are more examples coming from WIEHAG, that is this Austrian design office. About tree branching system structure, of course, they are very efficient since you are making the timber working in compression instead of flexion, and all the system reveal very efficient for different kinds of structure and of bridges with the Pont de Crais I mentioned already before. You have also this counterpart in architecture with water center in the south of France. Here you have kind of branching system that has been deployed, and a question arising from this is a question of connection that have to be developed inside the system to make it possible to run. And if the question of the course is linked to loads, that could be not a good approach if you have not very regular system into your connection. Of course, what's works very well is changing material going to steel. And from this, of course, the same efficiency can be met, but steel is working also in bending, and timber is not that efficient. Going to truss and lattice truss timber, again, the question of the connection will be important to look at. And depending on this, you can deploy kind of more or less complex truss system. Lattice systems are very interesting since they are developing several load paths into the structure. And you have contemporary example in this with the example from Laurent Ney, that is a Belgian design office that very famous in Belgium, but also all around the world, with one of the first work here developing lattice truss. You can see again a very simple truss system combined with a second truss system, and each time you have a connection, you are just lowering the length that would be that could possibly be buckling, and that's a way to make a very kind efficient system in that system. Sylvain will be analyzing this structure with VGS in some minutes. About fan-like structure, again, the Gruberman brother developed this kind of system. You can see here this kind of in between funicular and in between here a fan-like system appearing at the support for this quite a long bridge with the original drawing into this. That's a way to go to the very long span with this kind of massive timber material, and some specific drawing made by John Soane in this case. And that's a very nice application that has been made by Jörg Konzett that I mentioned in the very first lecture about graphic statics. And this fan system has been developed for efficiency of the timber. There's not that much material that's been used with this very nice timber design. So let's move to timber frameworks. We know that we have traditional frameworks that will be developing a lot of inventivity, and you see several examples of this. We have to inspire of this for the efficiency of our system, but we have also to have a look on frames that has been designed in Japan, in which we have systems in everything is working in bending, and in this case that won't be damaged by earthquakes. And this kind of assembly can be reused also sometimes, so that's a kind also a source of inspiration. You have a kind of Chinese counterpress of the width that's also dissiping the energy of earthquakes, and these are very stable systems that can last a lot of time and a long times. A short word about Corbel system that you mentioned already, with the Chinese interpretation of this, with this kind of bridge that I'm just finding fascinating. That's very nice to have the occasion to show the advantage of this kind of construction. Here we have a kind of modern reinterpretation of that bridge with a similar system. What about bending slab with CLT panel? You know already this system. You can develop a series of derivated initial product that can be implemented in this kind of structure that could be between bending and between plates and shear walls. And that's also something very interesting with the potential we can develop in such a structure. So it will be for me the end of this presentation, and I will be offering the screen to my colleague Sylvain Rasner that will be presenting some of these examples in an interactive way in VGS.
Thank you, Denis. Well, Philippe, can you just confirm how much time do we have?
Yeah, take your time.
Okay. Maybe I just switch off the camera because I'm just in the middle of the French Alps, so the network is not of high quality. Okay. So the idea of this last chapter of the presentation of today is to present some explorations of VGS. VGS, which is vector-based graphic statics, is a tool for informed and controlled design. As you were showed last week by Jean-Philippe, it's not a form-finding tool. It's more or less an analysis tool. And we are convinced with Denis, Jean-Philippe, and other teams of the other members of the research team that design of efficient structures, and wood structures also, can be addressed through manipulations of the structures with the aid of VGS. As a reminder of what you have seen with Jean-Philippe last week, VGS is a plugin for Rhino and Grasshopper, and you need to feed the plugin with some information. So the curves which are the edges of the structures, you need to feed it also with the loads, 1, 2, 3 load cases. Or more, and you need to feed it also with supports. And the definition, the parameterization of the supports is very important because it will give you the possibility of an isostatic structure. And if the structure is isostatic, it will be easier to manipulate it with VGS. If it's not isostatic, it's not a problem. You can also use VGS, but you will need to use the self-stress box that you see here in the middle. And it's a little bit more, let's say, complicated because you need to test the self-stresses possible to achieve the equilibrium of the structure. And then, as it is not a form-finding tool, you need to feed all that data, and the plugin will evaluate equilibrium if it exists. So if it doesn't exist, you need to parameterize differently the data to achieve the equilibrium. So once you have, let's say, succeed in an equilibrium at that step, it's possible to manipulate the form and the force diagram that you will that you see here on the right. All the definitions, let's say the visual representations, and the algorithmic procedure. So let's begin with an elementary case with a strut and tie model that Denis just has been showing. It could be, for example, a beam in CLT. Because of the anisotropy of wood, it's quite interesting to use CLT. And if we compute it with a Rhino, we compute it with Rhino, and we feed the data in the Grasshopper plugin, VGS. So we find a form diagram and a force diagram on which we can make some manipulations, and I will show you on the video. You can manipulate on the outer forces that you see in green, and you can see, as a consequence, the reactions on the structure. And you see that it's an, how do you say this? It's a real-time procedure. You see all the consequence on the form diagram and on the force diagram at the same time, and that's what is very interesting, because you can design with more information of the force diagram. You can design the form diagram, or at the opposite, you can design the force diagram with the information of the form diagram. So it's quite interesting to have the two reciprocal diagrams moving at the same time. You can also make some manipulations on the form itself, and here you will see my mouse, maybe yes, to try to make some manipulations on the portals of the truss, and to make some moves on the points of the bars. And you see again the let's say the dynamic procedure between form and force diagrams. A little bit more complex structure is the Koblenz viewpoint that Denis just presented a few minutes ago. This is a viewing platform located on a hill in Germany. The structure is made of wood, and there are posts of cotton steel anchored in concrete foundations. The plan of the building represents a triangle defined by 3 different spans, and the last set of those spans on the first ones. And this peculiar plan, this closed form of the structure, make it possible to avoid bracing frames. And that is let's say the big picture of the building, because it's very peculiar for this reason. So this is a lattice timber truss system. This is quite interesting because it's built, and it's both architectural and structural project. The section is the facade, let's say, and we can process some analysis with VGS. The species of the wood is Douglas, very classic, and the spans are crossed by lattice girders. Those lattice girders are made of 2 layers of diagonals. And those 2 layers of diagonals, just as Denis mentioned it, made it possible to refine the sections and reduce the buckling length by holding them at the crossing, as you can see. And then we can process the analysis with VGS and have the form diagram and the force diagram. As it's a quite complex structure, we can manipulate it a little bit, but not so much in just one single video. But I can show you some manipulations on the outer forces. Maybe you can note that the outer forces are not represented on the force diagram. It's one parameter of the VGS plugin. You don't need all the time to see all the elements that you can compute. So you see the explorations of intensity and directions of the forces. And again, the computation of the reaction forces in consequence. Let's move to a truss, not a lattice truss this time. So there are not connections in the middle of the diagonals. Here there are cables that suspend the bridge. This is the second version of Traversener 1. The Traversener 1 that is a bridge that collapsed. Not collapsed, but was destroyed by falling. The engineer from Switzerland built this second version, and the only viable option at the time appeared to be to move the bridge down the valley, closer to the river and further away from unstable inner valley. So moving in that direction, Conzet let's say, had to build this bridge in a very difficult site, where the north flank of the valley formed a very steep vertical work face. So the most obvious solution for this location was the suspension bridge spanning around 100 meters. And Conzet developed the idea of shortening the span of the bridge by making an angled walkway in the form of a long stair that we can see on this section. This arrangement allow Conzet to use the ribs of either side of the valley as natural pylons for a suspension bridge, and the bridge accommodates two drastically different elevations. And at the end, the bridge acts as a massive cross-laminated timber staircase suspended with cables. So at the end, the span is of 57 meters and not 100 meters with this methodology. We can see the form and the forest diagram of VGS, and they decided also, it's nice to mention that there is no anchor points, but more concrete foundation on the right and the left to avoid the anchor points and the difficulties to maintain them in the typical Swiss weather. So as it's quite a complex structure also, I just show you here some variations on the outer forces with the intensity and direction moving. And you can see that we can revert the directions and discover in this way the Stratton-Time model inverted also. Another example case study is this first version of the Traverse Enough bridge. So this is the bridge that was destroyed by Working Falls, and this bridge connects connects the both sides of a valley with a span of 47 meters and an inclination of 6%. What was very difficult with this bridge for Conzet was the self-weight of the substructure, which was very limited because of the helicopter available for the construction. So the bridge is very light, and it's a very light 3D truss system with paneled side rails acting as stiffeners that you see on the section. And the four sections that you see show the development of the cross-section of the bridge, mainly the connection between the balustrade and the substructure. So the deck is made of horizontal glulam beams and suspended with steel cables. If we see at the analysis with VGS, we can see the parabolic form that gives an advantage because the diagonal members are almost stress-free under permanent load, making them easy to replace if it's necessary because of the weather, again, in Switzerland. In this video, you can see a direct manipulation on the form diagram that reveals the complexity of this model, because you see the superposition of two submodels that I need to compute to let's say to manage to compute the hyperbolic structural model with the diagonals in two directions. So it shows you also, let's say, the limits of the tool that we are facing now and that we are trying now to overcome. Another video to show that the parametric models works well, nevertheless, with variations on intensity and direction of forces acting on the footbridge. No, it was not this video. Okay, this is the video with the variation on the intensity and direction of forces acting on the footbridge, and in one direction and then on the opposite, to see how the form diagram just adapt quickly with these variations. Okay, so the idea of this fifth case study is to analyze a fan-like system for a simple structure as this. This could be a CLT panel again, and if we analyze it with a VGS, we can see how the bars in compression enables the efficiency of the load path. And again, the video shows the explorations, variations on the acting forces, and evaluation of, let's say that the variation on the acting forces gives some evaluation of efficiency with the force diagram and the size of the graphical representation of forces. Again, the reaction forces and the acting forces, so the outer forces, are not represented on the force diagram, but you can make them appear with just a manipulation of VGS. Case study 6, a tree branching system. That's quite maybe a more funny case study. It looks like a spiral, and the definition is made by Yu Shishen just for us today to show the capabilities of VGS with this kind of 3D structure made of compression ring at the top and made of bars in tension to bring back the forces downward the structure. So we can see the form diagram, and now we can see the force diagram just aside and make some visualization of those two diagrams to show you how it is to just how easy it is to manipulate, let's say, the structure and the diagrams in the plugin. And some manipulations, I think. No, it's in this one. There you see the manipulations on the tree branching system with some manipulation on the reaction forces, and you will see also the manipulations on the form diagram and on the position of some points of the structure. You can see at the same time on the force diagram that it adapts automatically from the form diagram. And you could make some manipulations also on the force diagrams, but obviously in this case of analysis it's more complex to make because it's very it's not, let's say, obvious the moves you can make on the force diagram to make something quite good on the form diagram. Designer always prefer to, let's say, parameterize the form diagram. Well, again, a structure that Denis just presented a few minutes ago, a house made of cross-laminated timber panels. This is a single roof made of 6 gables roof. And this principle of 6 gables roof combined enables the architect to offer something like a free plan because of the span, but at the same time very specific sub spaces because of the roof that will stay visible from inside. So this is quite a monolithical roof seen as a folded, we can see it as a folded structure and we can parameterize it on Rhino and make it on it some analysis with VGS. You can see that it's quite a complex equilibrium that made me some headache to achieve, but the folded plates of CLT panels just appear in the analysis of VGS. We can see the ridges in tensions and the panels with diagonals in compression or the opposite from a side to the other side of the building. And this was the form diagram. This is the force diagram that we can see in video also, just to perceive all the complexity in 3D space of this force diagram. And we can make some direct manipulations. As it is an analysis, I'm not showing the form and the force diagram at the same time because it doesn't worth it because it is built as it is. But you can see that we can manipulate on the force diagram quite easily in the limits of the parameterization of the VGS. Okay, another case study, a little bit more specific because it is extracted from a research by design that we made with Denis and Jean-Philippe with some groups of students. The topic was an addition to the Queen Elizabeth Music Chapel in Brussels, which is, let's say, a center of excellence for artistic training with an international dimension in the music industry. And among diverse buildings to design, they had to draw a concert hall, and the structure of this main hall had to be integrated into the design process by the students from the beginning. So their task was to design, size, and draw their wooden structure. And this is the perfect task, obviously, for VGS and some extension, let's say, on parametric modeling that you can see, because VGS is just the box on the right of your screen. The other boxes are the, let's say, geometric definition of one of the results of this research task. So as a first result, you can see a folded roof made of CLT panels. Let's say same but different from Atlanta, because from the house of Atlanta that we have seen with the 6 gabled roofs, because it's folded, it can be seen as a folded structure, but it's very more systematic. And you can see the 3D model, the form diagram of one piece of the roof, very complex also to create and manipulate, but it works. It's a full 3D model, and you can see how the form diagram is in 3D. And at the same time, we can see the force diagram, which reveals behavior almost in 2D. It was one of the difficulties of those students to, let's say, solicit at the best all the bars of the truss. And other results of this exercise show diversity of structural models that reflect different approaches in the definition of the building, as they had to make it a whole of architectural and structural projects. You know, they had to make a project yes, as a whole, with the architectural side and the structural side. So they had to manage each group special procedure to make it happen at the same time. And there are so this is the explanation of the diversity of the results. Some groups use the superposition of 2D diagrams of form and forces, and this principle was used to manage the different loading cases. Again, in this case, and not in this one, where we can see an interesting truss structure in glulam. We can make also some explorations of the outer forces in 2D, as you can see here below. And what's interesting next, it's that VGS, if I can make a little bit acceleration. Well, what VGS, what I want to show you here is that VGS VGS allows also for a comparative analysis of the values of forces in the base of the Stratton-Tye model. And this can be node by node. You can see, again, node by node, using the vector-based approach of VGS. And then we can isolate some node and isolate the values of the forces in this node. Eventually, based on graphic statics diagram, timber joints can be designed according to applied forces because of this capability of the software. This led the video just shows the manipulation of the form diagram just plotted on this particular assembly, and it shows, I think, that VGS can be used to inform the designer about the transmission of forces in this node. And you can see that it's quite direct between the form diagram and the force diagram explorations, and you can just make it on Rhino. And at the end, it shows some bug also, because it's not always so easy. You see, up when I pick some point that let's say depends on parameters that I put in the Rhino definition, it can provoke some limits of the tool. And just to end, some other examples of joints, but that can maybe they can show some pitfalls as an inadequate bearing surface or difficulty in the management of different loading case. So those are examples of other students, but that show some limits in this very difficult exercise of timber-to-timber joints. And such an exercise, so as I just said, is very complex, but it can very well be informed with the use of VGS that you can see on those two videos at the same time now, where we can see how the VGS plugin can help the designer to balance the forces, to manage the different load cases, or to check the adequation of a bearing surface. Yeah. While I think it can be the end. I hope those explorations, those case studies show you how VGS can be used as a tool for controlled and informed design of timber structure. Thank you.
Thank you.
And again, sorry for the poor connection.
No problem. Okay, I think it's quite interesting, the VGS. We can have further understanding for that. I find VGS is more easily or more accurately compared to Polyframe, which developed by Monsat from UPenn, because last year we have a joint studio. So we compare, we don't have a very deep knowledge about the VGS, but in the future, I'm looking forward, based on our collaboration, Dennis, we can understand more deeply on the VGS. But I find it's quite interesting. The VGS actually control more precisely for the joints, not only the joints, but also the process of components, or all the joints, bars, and everything could be very accurately controlled. But at the same time, because the form diagram, force diagram is more difficult for the student and the users to understand, so that maybe need time to test it through the process, how the users can control this tool. So I would like to invite my student, because we have some postdoctor and the PhD candidates. They also research on this topic. So would you like to put forward any question from the floor to Dennis and Sylvain?
Yes,
Yeah,
I
Xinjie, please.
have one question. Yes, I have one question, and thanks for your lectures. And I noticed that at the beginning of the lecture, Professor Dennis mentioned that the bending is more efficient when it matches the direction of the fiber, and it followed by compression and tension. I noticed that in the example. Most of the components are in actually a compression and tension, and others some of the components are in bending. So I want to know and how do I consider this issue in the design process, because bending is more efficient and compression and tension is not so efficient than the bending, and also I realized that VGS in the design process may mainly analyze the type of compression or tension, but I think maybe it can be used in bending, or I don't know how to. Yes, and I just want to know how it is used in bending in this situation.
Okay, that's clear. So first, for the question, is compression or bending more efficient? The fact is clearly bending is not the most efficient. In compression or tension, you have all the fiber that's working the same current level. But the problem is when you bend the structure, you have a kind of fiber that are glued to the adjacent fiber that could redistribute force, and that could bring the fiber to work at a higher level and not being as a consequence suffering for the defect that are existing in the timber. So at the scale of the material, that's the answer, is that you can go to higher tension or compression force due to bending, since all the fiber are not at the maximum. And that's the key of the answer. As soon as you are solicitate all the bars in tension or in compression only, you have to lower to middle the rate to which you are able to put the fiber working. So that's just for the difference of force you can have at the local element. But as soon as you are thinking at the scale of the whole element, bending will drive to have deformation that you are not able to control. If you are just compression or tension force, you have very few deformation, and the structure is very more efficient. And this is why I try to gather a series of examples in which you are not relying on bending to go to maximum efficiency of the structural system. But also, if you remember this kind of table I showed about the several approach, depending on what you are seeking as an objective in your structural design, you have to go sometime to bending or to something else as corbel system or piling element for the question for earthquake, for instance. The fact is that as soon as you have triangulated systems, they are very efficient, but they are also they could be fragile if they suffer to solicitation as earthquake. The fact is that in Belgium we have nearly no earthquake. China is a wide country in which we have several scenario that could appear. In some time you have an earthquake and on the others not. So from this you have each time to make your mind about the direction you want to go and what could be the decisive element of design that will be enabled to design to the kind of structural system you want to deploy. So most of the time that's the answer. About VGS and bending, So you remember that the funicular polygon is just showing what's happening. So this kind of curve, it's showing what's happening in bending, but that's just a way to represent the problem. You can choose to just go to student time modeling, or you can choose to just go to the, let's say, the classical theory in which you have bending, shear force, and so on. And that's what I put forward also, that you have always to choose to take one or the other approaches. And of course, VGS don't manage bending, but you have to choose on the model, and you can model a beam as a truss system, or you can model a beam as the association of of a truss of an arch bars and a tension bar, or as the reverse, as a funicular bar with a compression strut. You can always choose your model. So that's not an issue for VGS. It's just an issue for your habits in looking to a problem. And we discussed this already last week about it's kind of complexity we are not used to. But if you have to learn about the classic elastic theory, that's also a kind of learning you have to do to be able to manage it. It's just a different system. And if you are going to listen to our colleague Joseph Schwartz, he would say bending is not existing at all. It's not true. You just have tension and compression. If you're looking to the stress, indeed you have just compression or tension. So that's another way to look at structural problem. And indeed, VGS is in this new way that is linked to a serious stuff about indeed 3D graphic statics, about student time modeling, about plastic design, about all the series of elements that I put forward in this series of lecture to make it consistently about what was the vision of the structure. So I hope that the difference between the local stress is clear. It's the same in concrete. In concrete, you have higher level and you have to limit only compression forces as you have column. That's exactly the same. So that's not truly relevant about this, but indeed compression is just more efficient, but it could be also more fragile depending on the circumstance of you are using them. So that's an interesting question about the structural design.
Great. Yes, I think it's an interesting question, and the answer is really, we need time to understand more deeply about the VGS. Actually, Dennis, in my team, actually, we're doing a lot of one-to-one scale mockup research. I think in terms of the complexity of the VGS tools, I think we should plan maybe to do different scale test in the future. Maybe from a very small bridge to larger scale and to real scenarios, real project, real prevalence. We have time. We have 3 years to understand. Sure. I think it's a really good toolbox and VGS. You already achieve a lot based on this fundamental tool set. I think in the future, I think because we have very strong robotic fabrication infrastructure system here, and that will help us to test different scenarios. Especially the timber structure is really good to test this kind of bar or compression system, compression tension system in the timber structures buildings. So I think it's a great opportunity to have you give us, Dennis and your team, give us 3 wonderful lectures. In the future, I think we should have more collaboration, including teaching. I would like to invite your team, maybe teaching not only in the workshop, the summer school workshop, but also could be the studio. And you have, you're welcome to travel to China, maybe for a semester, and then bring your student here. I think I will also invite you to traveling to see some timber projects, wonderful bridges you mentioned in the different countryside of China, beautiful countryside. And although it's hundreds of years, but we still have a wonderful timber project in China, including the tower, including the Ming Dynasty and the Qing Dynasty temples. I think the joints, Dogong joints, extremely beautiful, and we need people to research on that for the earthquake, for the timber structure joints, and also a lot of problems, a lot of scenarios. We have opportunity to make research together in the future. So any other questions? Because this is the last lecture this semester Dennis gave us. You're welcome to put forward any questions from you. Yes.
Hi, Dennis. Can you hear me?
Okay.
I can hear you. Yes.
Yeah. So thank you for your very professional and systematic lecture. And I'm really inspired by your initial research about the timber since it is a very traditional material, and until now we all know we have to innovate some of the different use and different composited use of this kind of material. I just have one question about this material. I just would like to ask, considering some of the structural performance of this material, and since it is a biological material, I wonder how can we explore timber in the perspective of material recycling and reuse, as well as its potential for combination with other biomaterials.
Okay, so thank you for this question. That's a very nice question indeed. I think that maybe the analyze the cycle of influence or the life cycle analysis. That's a true question in which we are attentive to. And the problem is that indeed that's a biological material, but as soon as you are treating it, it's not anymore biological material. So the end of life of the system is quite important. And as you have seen, the properties in the same scenario as drowning, as getting lower with the time. But normally, if you are changing the way the structure is assembled, it's a way of reinitiate it again. And so about this, that's a true stake, since what do you need for every structural system to be reused? It can be reused in place, or it can be reused after dismantling and rebuilding with the material. And so which are the conditions we need for assuring that it could be reusing without being damaged? And that's totally another way to design the structure and to disassemble it. And indeed, I hope that in the framework of the pavilion you have to design, we'll be able to think through to this question, or what could be a selection of timber you can dismantle and reassemble. In the classical architecture, with the example I mentioned, it is very frequently that structure has been disassembled and have been combined in another way. So if they could do it centuries ago, so 3 to 4 centuries ago, why are we not able to do it right now? So that's a true question about design. And I think that's a true architectural problem. So it's a question about manufacturing, assembling, and testing, and so on. But it's a question of an architect. And today, the architects are not trained to ask this kind of question. And I hope that with the experience you have, the experience we can have with the help of history and the help of tests, we can make our minds about what should be a structure to be fully reused at the end. Reuse could be also for timber just burnt, but if we have a chemical into it, it cannot be burned domestically. So that's a true question. And the first in this series is to know very, very well the use of material, to have no problem with water and with fire. As this can be achieved, we can discuss about recycling structure. If that cannot be achieved, your structure will be damaged along the time, and everything ends at that stage. So that's a research for engineer for structural system, but that's also a research for architect. And the architect have to master all this series. Just for the history, we have at the school 1 year just training about timber, and there are kind of other training. So for people having their diploma already, they are to be trained more and more about design, timber design. You can do it without this design, but if you do it without it, you are making just mistake, and there are a lot of mistake possible in timber. So about the perspective of one day being able to just reuse forever the same timber component, that's just fascinating. Maybe we can repair also with plug of timber that can be adapted to existing element. The question is cost. If the costs remain the same, maybe it's not that interesting. But if you see the properties of old timber that were just exceptional, you can always reuse them. So that's a kind of thinking we are not used to have about reusing this structure. But I would like personally very enter in this topic of design for reusing with timber, with efficient structural timber. And that's indeed a fascinating topics. Sure, stakes. Sure. I'm not sure I answered the question. Just tell me if this is not clear about this.
Yes, thank you very much. I think you just point out a different perspective of my question. It's not just to innovate the new material, but it's a problem of design of the structural efficiency design. Maybe I can study it later. Thank you very much.
And there are specific materials, condensed timber, and there are biological odor material that could be associated. That's yet another problem, and I'm not skilled on this. I'm focusing on design, so that's our approach.
Yes, thank you very much.
Thank you. Today, actually, Dennis make a very detailed introduction to the materiality of timber. I think this is fundamental knowledge we need to learn. We need to make research in the future. Actually, Gary is developing the two robotic teams. Actually, we have like 16 axes, two robotic on the track and can collaborating manufacture the very big pieces in Shanghai. So Gary is a developer for this robotic system, who is right now the PhD candidate. So in the future, he is also inside the team. And Xinjie Zhou, he is actually make research on the graphic statics and also achieve graphic statics in the timber structure. So he will also be one of the chief PhD researchers in this collaborative team. So in the future, I think we should have a lot to learning from your team. And also we want to sharing our infrastructure system and sharing our different research scenarios with you. And looking forward, next week, we'll have a special meeting to kick off the joint research. Where we should prepare for some plan and schedule and research plan and how to make different progress based on the collaboration of the pavilion research or the mock-up research or the including we can exchange the PhD students to each team and to learning from each other. So that's a great opportunity to have you here, and looking forward, Dennis, you can traveling more often to Shanghai in the near future. Okay, thank you so much for the fantastic blowing 3 fantastic lectures, and your team are fantastic. So thank you for your coming, and see you next week, Dennis.
So thank you very much for this
opportunity.
See you next week. Okay, thank you.
Thank you, Sylvain.
Bye. See you next week. Bye.
Okay. Bye-bye.